point charge in front of it. This will be a next example. Yesterday we have seen how to develop images, is it? So we are in this kind of situation. So you take a circuit, it's conducting in nature, okay, and you take a point charge, let's say charge plus 2. Okay? Clear? So now if so let's ground it. So this is grounded, it means the surface of the conductor, it's maintained at 0 potential. Clear? So what is our boundary condition? Phi on the surface, potential on the surface is 0. What is the potential inside the conductor? That's again 0, is it? Okay, because there is electric field inside the conductor is 0. Okay, so let's call the radius R. Okay, so let R be the radius of this conductor. So what I will do, okay, so I am having this charge Q, it's placed at a distance D from the center of this conductor. Let's call this distance. Okay. So now we are interested in finding the electric field, let's say at point P here. So this is our first Q charge, let's say point P. We are interested. Okay. So we need to figure out what is the electric field outside the circuit, because there is no electric field inside the circuit. Clear? So in this kind of situation, what I will do, I need to introduce an image charge. Clear? So at what distance I need to put? Okay, that we need to figure out. Let's call a point charge. Let's take an image charge Q prime here at a distance of, let's say, D prime. So okay, so you can think this as simply what? As a spherical mirror in front of you. So when you look, what will happen to the image? So it will not be exactly at the same distance. Okay, so it will be at some other distance. Clear? So let's call it is at a distance of D prime from this origin. Clear? And I need to figure out how much is this image charge. Whether this Q prime is same as this Q, or rather whether this Q prime is minus Q or something other. And what is this D prime? We need to figure out this D prime as well. At what distance I need to put this image charge such that I can reproduce my boundary condition. Clear? So what we are doing here, we are simply we are creating an image of a given charge, okay, so that we can reproduce the boundary condition. Okay, so in this very configuration, the boundary condition, you need to put phi equal to 0 on the surface. Okay, on that way, with that very help, you will be able to figure out what this D prime is and what this Q prime is. Clear? Okay, so let's orient our coordinate system in such a way that this charge lies along z axis. Okay, so I'll be having, let's say, origin of the coordinate system. So this will be simply the z axis. Okay, let's call this a z axis. Clear? So much sure? Okay. So this is a point P while we are trying to figure out what is the field. Clear? So let's draw. So let's say this at a distance of r. Okay. Use my notation of this. Clear? So what is the, okay, so you are, what will be this distance? It's r minus r prime. Sorry, r minus what? Okay, let's write, okay, so you call this as, let's say this is r prime, this entire vector. What is our r prime? Okay. Our r prime is simply dz in the z direction, is it? So it will be simply, okay, so let's write this vector. Okay, so let's put this thing. Can you tell me what this object will be? So it will be simply r minus g prime z. Is it? Because this is g This along z direction. Clear? 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 Is it understood, the diagram? Have you understood it? Okay, simply it is the, okay, so what is the vector along the, okay, so you are considering this line along z direction, is it? So the charge rests on z axis, clear? So what will be the unit vector? So it will be z unit vector along that direction. Oh, okay, so what is the vector? Position vector of this very charge? It will be d times z prime. Okay, what is the position vector of this q prime? It will be g prime z. Clear? Samajh? Okay, so this is our situation now. So let's write the coordinates of this very point. So x, y, z. This is an arbitrary point. We are trying to figure out the field. Okay. Now let's calculate the potential now. What is our potential? So we know. Now forget about the conductor. Forget about the surface for the time being. Okay. What is the potential at point P? It is the potential due to this very charge and the potential due to this charge. Clear? So let's write it. So it will be something q divided by, let's write r minus r prime. So that's actually dz, okay, plus q prime by r minus d prime z. Okay? Clear? Now if you see this vector r, okay, this vector r subtends the same angle with d prime z as well as dz, is it? Samajh? So you are having an angle, let's call this angle as theta. So it subtends this theta with the z axis. Let's use spherical polar coordinates. So it is q divided by, under spherical polar coordinates, what this will be? So it will be simply r square plus d square minus twice r d cosine of theta plus q prime divided by root of r square plus d prime square minus twice r d prime cosine of theta. Okay, why theta in both cases? Because the angle is subtended by dz and d prime z, they are the same, is it? So that's why the same angle. Okay, so this is the potential at point P. What is unknown in this very potential? What is unknown? Q prime is unknown and d prime is unknown, is it? So how we can figure it out? We need to, we will apply the boundary condition. Okay, what is the boundary condition? Okay, so the boundary condition is that, so let's apply the boundary condition. Phi at surface when r is equal to capital R, when, okay, on this very surface, what is the potential? It's equal to 0. So this is our boundary condition. So which implies therefore this q divided by root of r square plus d square minus twice r d cosine of theta, that's equal to minus times q prime root of r square plus d prime square minus twice r d prime cosine. Clear?
Capital R.
Oh yes, it is capital R, sorry. Yes, great. Clear? So now let's multiply, cross multiply the terms and square. So you will be getting, okay. So I will rub, so let me, so you just cross multiply things. So you will be having this very objective. Let me write q square r square. Let's write, okay, squaring q square r square plus d prime square minus twice r d prime cosine of theta. Okay, then take the another term, okay, minus q prime square. Okay, so you multiply, so it is r square plus d square minus twice r d cosine of theta is equal to 0. So this equation is valid for any theta, is it? No. So when you square it up, so it will be plus, is it? So it will be q square divided by this thing, q prime square divided by this object without root. So then you multiply and take this on this side, you will be having a minus sign. Clear? So now let's separate the terms. Okay, so I will put it in this fashion: r square 1 minus q prime by q whole square, like this thing, d prime square into 1 minus q prime d by q d prime whole square. So just rearrange the terms in this fashion. Minus twice r d cosine of theta, okay, 1 minus q prime by q whole square, okay, d by g prime. Clear? Okay, so now this equation is valid for any theta. Okay, so that means we need to put the coefficients of the cos theta equal to 0. So it means the coefficients of this cos of theta, it is equal to 0, and this term has to be equal to 0 identically. Clear? So it is the same case, ax plus b equal to 0. So if it's valid for all x, for arbitrary x, it means a is equal to 0 and b is equal to 0. So this gives, so this equation is true for any theta, so which implies this very object r square into 1 minus q prime by q whole square, okay, plus d prime square 1 minus q prime d by q d prime whole square. So this is equal to 0. So you'll get two equations, and twice r d 1 minus q prime by q whole square d by d prime, that's equal to 0. Since this is not equal to 0, these are non-zero terms, it means this very object has to be equal to, let's solve this thing. What you will get from this equation, so this yields, okay, so what you will get, so you will get q prime square, that's equal to simply 1 is equal to this thing, so you will get q prime square in terms of, so q square d prime by, okay, just use q prime square in this very equation and figure out, okay, or you can use q square or d prime, or okay, q square by d you can use in this very equation, okay, use this very equation. What you get ultimately, rather you need to, okay, this way you just solve these two equations, the solution which yields, the solution of these two equations, you will get two equations yesterday. We got two solutions, is it? One was physical, another was unphysical, is it? So the only solution which gives you the physical boundary condition, the solution which reproduces the boundary condition, is you are having this d prime is equal to r square by d, okay, and q prime is equal to minus q r by d. Okay, if you substitute d prime as this thing and q prime as this much, so you will get potential on the surface equal to 0. So you will be getting other possible solutions as well, but they will not reproduce what? The boundary condition. Clear? So this is the only solution which will give you what? Which will reproduce the boundary condition. Okay? So therefore I can write, so now let's write. So if you look here, so you don't get actually the full charge, is it? So what you get? You don't get the minus q, you get actually minus q times this very factor. So that means the magnitude of this very image charge is not same as this very charge. Clear? So think in terms of your, okay, you look into the spherical mirror, what happens to your image? Either it will be reduced to some, okay, yeah, some smaller image, or it will enhance to a larger size, is it? Depending upon which kind of mirror you are in front, is it? But only in case of plane mirror, you will get the same image. You got my point? Okay, so that's exactly happening. So this amount of charge will not be the same. Okay, and what is d prime? So you are getting it as r square by. So it's not exactly the same distance. So much, yesterday we have seen in case of the plane mirror. Okay, so you got the image at the same distance from the mirror. Clear? Okay. So now let's write it. So now we forget everything. So just write the solution. So what will be our phi of r? Let's write this phi of r. So it is simply q 1 divided by r square plus d square minus twice RD cosine of theta and root. So 3 by 2. Right? No, it's on the then minus 1 divided by root of yes. We need to simplify it, yeah? Okay, so what was our formula? So let's write my formula. So the first term is as q divided by root of r square plus d square minus twice rd cosine of theta. Then you are having what is now q prime? Q prime is minus q, this r divided by d multiplied by 1 divided by root of, so root of what? R square plus d prime square, is it? So it is r square by d whole square minus twice r d prime. What is d prime? So it is r square by d, okay, cosine of theta. Clear? So this is the potential. Clear? So you can write it in this way, simply q into 1 divided by r square plus d square minus so let's simplify it a bit. Okay, r minus twice r d cosine of theta, okay, raised power half, okay, minus, so you are having q into r by d. Let's simplify this very root. So what it will be? Let's take d square common, okay, so it will be root of, okay, so it is d square r square plus r raised power 4, okay, minus twice r, so what it will be? D r square cosine of theta. So when you take 1 by d square out, so it will be simply 1 by d, and this will cancel this will out. So it is simply q you take out, so it is 1 divided by r square plus d square minus twice r d cosine of theta and its root minus r divided by root of d square r square plus r is by 4 cosine. Okay, now let's put this small r is equal to capital R. Okay, if you put small r equal to capital R, what will happen? So potential should be equal to 0, will it? Okay, now let's put, it will be r square d square minus twice r d. Now when you put capital R, so what you will get? So you take then r square out, is it? Out of the root. So that r and r will cancel out. You will get in d square plus r square minus twice r d. Okay, cosine of theta. This will cancel it. This. So you will just check it. So it is not that difficult. So it is simply equal to 0. Okay, so that means this solution is valid. Clear? Okay. So this is the potential at some point P. Now let's try to figure out the electric field. Now if you see, this potential depends on both r and theta, is it? So it is having angular dependence as well. Clear? Okay. So let's try to figure out what. Okay, let's go to the nearby. I mean, so this very point at which I am trying to figure out the electric field. Okay, so let's say this point is in the neighborhood of this very surface. Let's try to figure out what is the amount of electric field or what is the magnitude of the electric field on this very surface. Clear? Because I have induced a charge within the conductor. So that means I will be having what? An electric field, some kind of electric field on this very surface. Clear? So I will just calculate the electric field on the surface. Okay? So this I am interested in. So you calculate simply the electric field at R is equal to R. Now let's look here. Since this potential is having phi dependence, is it? Sorry, theta dependence. Okay? So you are having a radial dependence, R dependence, and a tangential dependence, theta dependence. Now let's check about the theta, this component of the field. Clear? So if I look at here, what is the tangential component? Since field inside is equal to 0, is it? So what about the tangential component? So since tangential component is what? Continuous across the boundary. So it implies E theta at the boundary should be equal to 0 because it is the tangential component. So you will be having what? So this will be 0 because of the boundary condition. So only the component which will survive here is the normal component, radial component. Since radial component is actually perpendicular to the surface. Got it? So this will be the only non-zero. So if I try to figure out now the electric field at surface, so it's only the radial component which is contributing. Okay? So therefore I will write this electric field at, let's say, R is equal to R. So that's simply minus del phi. You calculate it at where? R is equal to. So it means there will be only what? R component contributing to the field. Okay, so I will write simply this R partial by partial R acting on this phi evaluated at where? R is equal to R. So if you are far away from this very surface, E theta will not be 0. You got my point? So E theta will be what? Non-zero. So in that case you need to calculate what? So you can write simply this E is equal to minus nabla phi. So what you have to do? So R partial by partial R plus theta partial by partial theta. So you need to calculate both the components. Okay? So let's put this as a home assignment. So just calculate this object. So I'm only interested in where? The surface. Clear? Okay. So you just differentiate it. Okay, once you differentiate it, okay, so you will be getting this electric field on the boundary. R is equal to R. You will be getting simply minus Q B square minus R square divided by R into B square plus R square minus 2s dr cosine of theta is called 3 by 2. Clear? So this is the amount of electric. I have just differentiated it. Yes, any question? Okay, so this is simply the differentiation of your phi and substitute R is equal to R, you will get this formula. Okay? Okay, so now what is the induced charge density? Okay, what is the induced charge density? Can anybody? Okay, so what? How much is that? Let's call this as inducer. So it is simply electric field. Can you tell me? Just tell. So it's 1 by 4 pi. It's actually 4 pi times this thing. R dot E above minus E below. Is that true? So this below is equal to 0 and R dot R will be equal, so there will be a unit vector. So it's simply 1 by 4 pi and there is a minus, okay, Q into D square minus R square divided by R into D square plus R square minus 2s dr cosine of theta raised to 3 by 2. Okay, so this is the induced charge density here. Okay, so now let's calculate the total charge. So I need to calculate how much is the total charge. We have actually seen that. What is the amount of charge on the image? Minus Q times. Let's calculate it from here. Okay, so let's calculate the total charge. Since, okay, when I calculate the total charge, my surface is fixed, is it? So the radius of the surface is fixed. What is the, and now the element, line element on the surface? So surface element, tell me, sorry. What is the surface element? It will be simply R square, capital R square, sine theta, d theta, d phi, okay? So therefore, charge induced, total charge induced, it will be simply, okay, integration over surface. So it is R square sine, okay, let me write first, it will be something. So you, ds prime, sigma, okay, ds and sigma, okay, sigma induced, so integration over what? the surface. What is our surface here? So it's integral r square sine theta d theta d phi. It is the surface element. Okay, and then you are having sigma at r is equal to r. Okay, theta and phi. Since this is already calculated where r is equal to r, I mean it's on the surface. So let's integrate it out. So you will be having, what is this thing? Okay, so you have this capital R square. Okay, then you are having minus 1 by 4 pi R. Okay, there is a Q, a D square minus R square. These are constant numbers. Okay, then you are having, okay, integration over phi, because there is no phi dependence, you will get a 2 pi. Okay, then you are having integral sine of theta from 0 to pi d theta divided by this object d square plus r square minus twice r d cosine of theta, that is what 3 by 2. Here what you do, you simply put cosine of theta equal to, let's say, x. So you'll be getting what? Sine theta d theta is equal to dx. Okay, so you'll be converting this simply into dx divided by d square plus r square minus twice r dx, is it? Got it? Raised for 3 by 2. It's a simple differentiation, sorry, integration. Okay. So I'll write, so you'll be getting q induced, let me write that. So it's minus q into d square minus r square, okay, into r divided by 2. So you will get 1 divided by dr, then you are 1 by integration of this thing, right? D square plus r square minus twice this rd. Then let me write x, no, minus 1. Okay? So I just skipped many steps. You just put actually cosine of theta is equal to x. So sine theta d theta will be simply dx, clear? And limits of integration will be simply minus 1 to plus 1. These kind of integrals you need to know. Okay, so these are simple integrals. Okay, so what I will be getting, minus q into d square minus r square by 2d. Okay, so you will get d plus r. Okay, clear? Got it? So what that is equal to, just solve it. So it's minus q into r, right? So once you solve, figure it out. So it will be q into r by d. What is this equal to? So it is same as what is our induced charge, is it? Clear? So now let's calculate the force of attraction between the charge and this very conductor. Okay, because you will be having a negative charge on the conductor, is it? So what yesterday we had done, how we have proceeded for the force. To calculate the force, you just ignore the sheet, okay, infinite sheet, and just calculate the what is the force between the induced charge and the charge, is it? Similarly, we will just ignore now the sphere. Okay, let's ignore the conducting sphere. You will be having now the charge. Okay, so force of attraction we can calculate. So how you do it? Just ignore conducting sphere, okay, and apply simply Coulomb's law. Okay, so what is the force of attraction? So it will be simply F. So what is the charge? So one charge is actually Q prime, another is Q. What is the distance between the two? Okay, if you remember, what is the so you are having, okay, so this is at a distance of d prime, is it? Okay, so you are having Q. So this at distance of d. So the distance between two is what? D minus d prime. Okay, so it is simply d minus d prime whole square. Clear? True? Okay, so now what is our d prime? Okay, let's write what is our q prime. So it's minus q capital R divided by d. Okay, multiplied by this q. What is d prime? So it is r square by d. Okay, whole square. So now let's calculate it. So it is minus q square r by d. Okay, so it will be simply 1 divided by d square minus r square whole square. Okay, so you are taking 1 by d out, is it? So it is 1 by d square. It is true. So what is that equal to? What is the force of attraction? So it will be simply minus q square, 1d will go dr. Okay, so let me write rt, so that you will not get confused with the differentiation. So this is what? Force of attraction. Okay, what is, so there is a direction, because let me put the magnitude. So what is the direction? Anybody can even tell me what is the direction? So it's along z direction. Patient? So it's along z. So now you can calculate how much work you can do. So you can figure out the work done in this kind of potential. Okay.
Along negative side.
Negative sign, it's the force of attraction.
Direction positive to negative. My negative direction side. इसकी direction से force.
So it will the positive charge will you can think it both ways. So if you are at the, let's say, on the positive charge, negative charge will get attracted towards you, is it? Or if you are on negative charge, positive charge will get attracted towards you. It's how you observe things. Since we are looking this kind of force from the perspective of the conductor, okay, so you are having a negative charge on the conductor and you look at the positive charge and it will come to you. Okay, it will get attracted towards you. Got it? Okay. So now let's take another situation. So this is, so is it clear now how you can apply the method of image? Okay, so now let's take one more example. Okay. Okay. So third example is, so you are having, now let's take two infinite conducting planes. Okay, they intersect orthogonally at some point. Okay. Let's take this point as origin. So we are in xy plane. So this is in the xy plane. So what is that? Z equal to 0. So xy plane means z equal to 0. So much one. So these are two conducting planes. So x plane and y plane. Okay, let me put some shade on this thing. It means these are grounded. Okay, so think of two mirrors. Okay, so these are infinite in extent. So let's put a charge here. Okay, let's put a plus charge q here. Okay, at a distance, let's say x distance is d1 and y distance is d2, and what is z? So it will be 0 because we are in the plane, is it? So when you are in a plane, so let's say z equal to 0 plane or in the xy plane, where the image will be, both all the image will lie where? In the xy plane. Since I am keeping the charge in xy plane, so the image will also lie in the same plane. So when you look in front of a mirror, where the image exists, so in the same plane, let's take the vertical axis is the z axis, so image will lie on that axis. Okay, on that kind of plane. Clear? Okay, similarly here, this is the xy plane where the image will lie. So it will lie in the same plane. It will not go, image will not go in the z direction. Okay, here z coordinate is 0. So much on, it's a planar geometry. You can take another axis, let's say. Okay, let's take the another axis, z plane as well, that's the conducting in nature and grounded. Then you are having a three-dimensional problem. Okay, then you will be having image all everywhere. So much on, you will be having image in all the three directions. Clear? But I will assume only the these directions. Clear? So now what I need to do? So we have just learned one conducting plane, is it? Forget about this very plane. Why okay? If what is the distance here? It is d2. What is the distance here? d1. Is it? Well, x direction is d1. Huh? Will you catch here? Okay, good. Okay, now let's forget about this very plane. Where will be the image? Just tell me. So in order to satisfy the boundary condition, I need an image, is it? So where I should place that? So below this very charge, at how much distance? At the same distance, because it's a plane, is it? So what will be the nature of charge here? Minus q. Clear? So if I forget this plane now, what is the image of the charge? So I need to put it at how much distance? Minus, okay, so d1, okay, so minus, clear? Samajh now? So what is how much charge you have? No, you have induced more than the charge, is it? So you have induced minus 2q charges, but total amount of charge is only q. So the charge neutrality is not there, is it? So when you consider both the planes simultaneously, you need to put one more charge, okay, so that you are having a charge neutrality. Okay, so we will put that very charge, let's say, along this, you can think the image along this very corner, okay, let's call this as plus. What is the total net charge of the system? 0, is it? So how many images I have created? 3 images. Now I need to check whether the images I have created, does they reproduce my boundary condition or not? What is the boundary condition? Potential on this plane is 0, potential on this plane is 0. If I am having this kind of system, okay, let's check whether the potential on this plane is 0 and the potential on this plane is 0. Let's check it. Okay, if this is 0, that means the images I have drawn here, they are correctly placed. Samajh hai? Okay, in the previous problem, what we have done? We have created an image and calculated the potential due to both the charges, is it? Image and the parent charge, is it? Samajh hai? And then we have applied the boundary condition, okay, to figure out what are the distance. But here I am already drawing, these are the images, is it? Okay, and now I want to check whether they reproduce the boundary condition, whether the boundary condition is satisfied in this case or if this is not satisfied, that means I have not placed these images properly. Clear? Or in other words, I have not written image properly. So if it is equal to 0, let's say potential on this is 0, also on this plane is 0, so that means I have placed my image properly. Clear? So this is the way we can do it. Okay, now tell me what are the coordinates of this very charge. So you are having minus d1, okay, then d2, then 0, is it? What are the coordinates of this very charge? Minus d1, minus d2 and 0. What are the coordinates of this very charge? d1, minus d2 and 0. Is that true? So these are the coordinates of the charges. Okay. So now let's calculate. Okay. Okay. How much distance is this? So this distance is twice d2 and this distance is twice d1. So now let's calculate at an arbitrary point in 3 dimensional. Okay, so you need to calculate the potential at point P, which is having coordinates x, y and z. Okay, now let's calculate what is the potential on this very plane. So that means if I calculate the potential on this plane, what I should get? 0. Is that true? So let's do it. Let's take potential on. So if I take, let's check. Okay, the boundary condition. So let me calculate the potential on x is equal to 0. Okay, then you are having y, you are having z. Okay, so when I am putting x equal to 0, what it means? So it's this very plane. Samajh? Clear? So I need to calculate what is the, you are at some point, okay, and you need to calculate what is the potential on this very plane. So what it should get? What I should get? 0, because potential on the plane is 0. These are the grounded planes. Clear? So now let's calculate it, whether it is really 0 or not. Okay, so I will take first this q charge divided by the distance between the point on which I am calculating. Let's call that point as x, y, z. Samajh? Now what is the distance between the 2 points? So it's x minus d1 square plus y minus d2 and z minus 0, is it? So because I am taking x equal to 0, so x will not appear. Samajh? So it will be like this thing, root of d1 square plus y minus d2 square plus z square. Is that true? So at a point P, so there is x is equal to 0. समझ में? So when I am taking at a point P x equal to 0, it means this point is here on this very line. समझ में? Okay. So then take another charge, that is minus q divided by root of. Since x equal to 0, so it will be simply d1 square plus y minus d2 square plus z square. Okay. Then you are having another charge plus q divided by root of. So x equal to 0, so it will be simply d1 square plus y plus d2 square, because y minus d2, okay, plus z square, okay. Then minus q divided by root of, okay, d1 square x equal to 0, then plus y minus d2, so it is y plus d2 whole square plus z square. So now look here, this term cancels with this thing, this cancels with this thing. What is the potential? So therefore I am having is phi x equal to 0, y, z, that is equal to, that means I have reproduced one boundary condition. Is it? So with respect to this plane, that means the arrangement of the charge is okay. Clear? So now let's calculate with respect to this plane. Have you written it? Huh? Okay, just write it. Any question? So now let's take, okay, so let's take, so I'm having some point P, X, Y, Z. So let's take another point. So let's calculate phi of x is not 0, y is equal to 0, z. So why is that? So it is this very region, huh? So this very plane, huh? Clear? So when I am putting y equal to 0, it means this very line. Okay. So now let's calculate now the potential. So calculate it. So what I am having? So q divided by, now y is equal to 0. So it will be x minus d1 whole square plus y minus d2, because y is equal to 0, so it will be simply d2 square plus z square. Then you are having minus q, the another charge, so it will be root of, okay, x plus d1 whole square plus y minus d2, y is 0, so it is d2 square plus z square, then plus q divided by root of, okay, now tell me. So it is x plus d1 whole square plus d2 square plus z square minus q divided by root of x minus d1 whole square plus d2 square plus z square. Okay. So this term cancels with this thing. This term cancels with this thing. What is the potential? That's equal to 0. Therefore, phi of x, y is equal to 0, z equal to 0. It is equal to 0. So that will reproduce boundary condition on both the planes, is it? So it means the image structure what we have created, it is correct. Clear? So much. So now let's write the potential. So have you written it? Write it quickly. Get me some water. Okay, so therefore I can write the potential at some point P, let's call x, y, z. So we'll write potential at an arbitrary point. Now tell me why. Okay, so the field will be non-zero where? Just tell me, why will the field non-zero? So on this very region, because this is a grounded plane, so on this very region there is no field, is it? So non-zero field will be only in this very region for an arbitrary z. Clear? You got it? So the same thing, you are forget about this very plane, where will be the field? Below this very plane, field is 0. Non-zero field is here. Similarly, on this side, the field is 0 because it is grounded, no charge is there. So field will be here. Clear? So a non-zero field will only arise where? X greater than 0, y greater than 0, and for an arbitrary z, because that point is arbitrary. we are taking the three-dimensional plane, three-dimensional structure. Now let's write first the potential. So it will be simply Q divided by, now tell me, so it will be simply x minus d1 whole square plus y minus d2 whole square plus z square. So this is the potential due to the original charge. Then you are having potential due to the image charges, root of x plus d1 whole square plus y minus d2 whole square plus z square, then plus q divided by root of, now tell me, x plus d1 whole square, okay, plus y plus d2 whole square plus z square, clear? Then minus q divided by root of, okay, x minus d1 whole square plus y plus d2 whole square plus z square. So this is the potential due to this very configuration. Clear? So Muzzafar, that means at any arbitrary point x3 of x, y, z, so the potential due to this very assembly is that. Clear? So Muzzafar, now let's calculate the field. So what I will do, I will just calculate the field near the surfaces. So Muzzafar, so at any, okay, how you calculate now the field? Okay, so let's say this is the home assignment for you people. So what is the field, electric field? So it's minus gradient of phi. So how much is that? So it is minus x partial by partial x plus y partial by partial y plus z partial by simply the differentiation, is it? So it's simple differentiation. Clear? So just so you will get the electric field in x direction at an arbitrary point. Clear? Electric field in x direction, electric field in y direction, and electric field in z direction. Okay? Got it? Now let's calculate electric field, I mean in the regions. So let's take, since the field is non-zero only where? In this region. Clear? So therefore, okay, let's take this thing. So for x equal to 0 and y greater than 0. So where I am, just tell me. When x equal to 0, y is positive. Where I am? Huh? So when x tends to 0, what does that mean? Huh? So that means I am actually in the neighborhood of this area. So it's not actually, you can take x tends to 0 plus. So that means I am actually on the neighborhood of this area plane. Samajh? You got my point? So it means just put, okay. So I can write it like this thing. So electric field in the neighborhood of this very plane. Okay. So you take simply x tends to 0 folks. That will be better. Exactly. So I need to simply, okay, so because there will be no x dependence in the potential, is it? Potential does not contain any x dependence. So you just then differentiate it. So will there be? So you need to actually calculate electric field this way, okay? So I will just put the limiting case. So it will be simply, so you need to calculate this way. I'll just put the limiting case. It will be this. So this is very simple. I think it should not be too difficult for you people. So it will be simply d1 square plus y plus d2 square plus z square raised to power 3 by 2, okay, minus 1 divided by d1 square plus y minus d2 square plus z square raised to power 3 by 2. Okay. Similarly, if I take, okay, now let's take this electric field like this thing, x positive, y tends to 0 plus, and z. Okay, so you will be getting this kind of field, twice q d2y, okay, 1 divided. You need to differentiate. It is a simple differentiation, okay. D2 square plus z square raised to power 3 by 2 minus 1 divided by x minus d1 whole square d2 square. Clear? So this is the electric field in this very region. Now you can calculate the surface charge density. Okay, so that you have seen Okay, you can calculate the surface charge density and then you can calculate the net induced charge. What is the net induced charge? Minus q. You are having 2 minus q's, is it? Minus 2q plus 1q. So that's minus q, is it? So that we are seeing. You can calculate it, eh? So there is no problem. So if you need, it is all done on notes, so you can get it. So it's a simple exercise. Eh? Okay, you can also calculate the induced charge. Okay. So how much time is remaining? Do we have? So yes.
If the angle between these two mirrors changes,
Huh.
like change of number of image charges.
Yes, number of images will change. Huh? So you need to introduce arbitrary number of charges then. So you need to calculate how many images you have. Okay, let me tell you this way. Let's. So there is actually a formula in optics. So how many images you can create if you are having two mirrors inclined at an angle, is it? So that way you can calculate the number of point charges, your image charges. Okay. So let's say if you are having this kind of. So these are two parallel mirrors, is it? So you put a point charge here or an object here. How many images you will create? Huh? Infinite. So it will be actually n number of charges, is it? So that means you will be having on this side one plane, another plane, another plane, another plane. Okay? Similarly here. Okay? Like this. And so you need to consider all these charges. I will be doing this kind of problem, but from the Green's function method. Okay? Got it? So we can do, okay, although I will be utilizing the same concept, infinite number of images will be there. Okay, I will be adding them up. Okay? Got it? So this kind of problem we'll be doing here. But once I teach Green's functions. Okay? Similarly, if you are having these inclined, so you need to check how many images you can have. Okay? Okay. So what is our this Tij? Anybody? So it's actually Ei, Ej plus Bi, Gj divided by, I think, so let me write out the value. So it's this way. 1 divided by 4 pi minus this thing, okay, plus delta Ij by half E square plus B square. Okay, so this is our Maxwell's stress tensor. Okay, now let's take a simplest example. So let's use it. First, let me do the complicated one. Okay, so let me do the complicated one, then I will take the simplest one. So, because in the simplest of the case, you will have certain things you have to do yourselves. Okay, so that's why I will start with the complicated one. Let's think of a charged hemisphere, solid sphere. Okay, so you are having a hemisphere. Okay, so it is charged. So it's a solid hemisphere. So you are having solid hemisphere of radius, let's say r, carrying charge. Okay. Now the question is, what is the force exerted by this? You are having actually, if you are having a charge here, so that means there is a charge density. If you are charge, that means charge density. So in other words, what is the amount of force that this charge that exists within this receptor it exerts on this hemisphere? Sorry, on the North Pole. So let's orient our axis along. Okay, so this is our z axis. Clear? So this is our z direction. So that means what is the net force on the North Pole of this hemisphere due to this very charge, is it? So you can simply do it Coulomb's law. Okay, you can calculate the electric field and you can calculate the electric field at any point on the North sphere due to this very charge distribution. Okay, and then multiply the charge, how much charge is there, and you calculate the force, is it? So you can think a point charge here and then you can calculate the force. This is the simplest of the way you can do it. But let's apply the stress tensor, Maxwell's stress tensor. Okay, this Tij, if you see, this actually gives, if you multiply it with the surface. Okay, if you remember the formula, okay, let's say partial by partial t integral of, okay, integral of, so t0 I dv, that's equal to minus integration over the surface, a closed surface, tij dsg, where s is some surface. Okay, so this is actually the momentum that crosses the surface. Okay, momentum that is changing within the surface, is it? And this, if you are having this as the changing momentum, this is the flux, is it? So what is that then? So this is the rate of change of momentum. What is that equal to? Force. Samasha, in other words, so this will be actually the amount of force that's exerted on a given surface, or the pressure that's exerted on the surface, is it? So that's the force. Is it? Samasha? So it means this Tij, this stress tensor, if you multiply, stress, it is simply the stress, is it? Stress on the surface. So if you multiply stress by the area, what it should give me? Force. So much that is the stress is defined as force per unit area. That's actually the pressure exerted on the surface. So much. So now if you are having charge here, the charge here, so it will exert actually the pressure on this very surface, is it? So much. So let's try to calculate it. What I need to figure out then? Since I am in the static case, B will not contribute. There is no magnetic field. Only the electric fields will calculate. Okay? These will contribute. Now there will be the contribution to this very force will come from two surfaces. In this hemisphere, since this integration over the what? Surface. So how many surfaces are involved in this very case? There are two surfaces. One is the hemispherical portion. Let's call it as a ball. Okay? Another is what? This very circle, is it? Let's call this as a disc. Clear? So much on? Got it? Huh? So you are having a positive charge on the surface. Now what is the direction of the force will be having? Now tell me, what is the direction of the force? Okay, so it will be in the z direction, because I am considering the force exerted on the north pole at this very point. Samasha, it is along the z direction. Clear? Now tell me, what is the surface? Okay, what is the direction of the surface? Because I need to calculate what is the surface I am taking, is it? So what is the direction of the surface? Huh? What is it? Okay, so let's put this I equal to z, because I am considering the force along which direction? Z. So let's put this I equal to z. So it will be simply z, then it will be z, is it? So then J I need to consider. What are the surface elements, is it? What is the direction of the surface? Now if you look at this very surface, so on this very disc, what is the direction of this very disc? So it is like this kind of disc. So let me put. So you are having a disc, or think of a circle. So what is the direction of this very circle? So it will be outwards. You think a cup like this thing. So this is the surface, the circle. What is the direction? It's along z, is it? Rather the opposite to z. You are having z in this way. The direction of this disc will be opposite to it. So you got my point. Now tell me, what is the direction? Okay, so that means only the z component of the surface is contributing. Or if I take, okay, so if you take, let's say this area is along z direction. Clear? Just learn this problem. Huh? So this is the z direction. It means this area, let's call this area, so it's along what direction? Bz. So that means I need to consider, if so for that very surface, only on this disc, if I need to calculate the force due to this disc on this very north pole, this very point, I need to then consider only Tzz, because I am considering the surface along which direction? Z direction. Clear? So for this very region, I need to consider only which element? Tzz. Clear? Now look at this very surface. Now let's take the hemispherical surface. So now I need to figure out what are the components of T I need to consider. Since this is a three-dimensional surface, how many coordinates are involved? 3 coordinates, x, y and z, is it? So that means this J will go from x, y and z. So that means I need to consider the components of the surface along x direction, along y direction and along z direction. So much, you got my point? Because if I take the patch of the surface area element, let's say this is the direction. Okay? So since the small element of the surface is what? It's a vector quantity. Okay, at least it's a vector quantity. Okay, so it will be having the components, a component along x direction, y direction, and z direction. So for that very matter, I need to consider then which components for this very surface. So I need to consider tzx, tzy, and tzz. Is it? Because I am considering the three-dimensional surface, and so this force is only along which direction? X direction. If I need to consider the force along, let's say, this force is along z direction. Okay, if I have to consider force along, let's say, x direction, what it would have been? X. It will be x and j. Then I need to consider xx, xy, and xz. Got it? So this is how we apply this very equation. Now let's go to the calculations. Huh? Clear? So the calculations are now simple. Huh? So let's take. Huh? Okay. Okay, so let me write now P, since this is so this is equal to 0 because B is not there. So what I need to consider? Let's calculate Tz. How much is that? 1 by 4 pi. So minus Ez plus what is delta Zz? That's 1. So it is E square plus B square is not there. No. So it's E square, right? So how much is that? So it's 1 by 4 pi. Okay. So E square is Ex square plus. So this object I can write as Ex square plus Ey square plus Ez square. What is this in? Ez square minus half. So it's, okay. So when you so it's simply half of okay Ex square. Yes. Second. Ey square minus. Okay. So that how much is that? 1 by. Yes. Yes. Just tell me. Okay, are you getting it? Huh? So this is Tz. Now let's take T. Okay, what I need to another consider Tzx. I will give okay Tzx. Okay, so when you put I equal to z, j equal to x, so these are off diagonal. Huh? So delta I not equal to j, that's equal to 0. So you will be having simply minus 1 by 4 pi Ez and Ex. And then you are having Tzy, that's again minus 1 by 4 pi Ez and Ey. Clear? So these are the components of the tensor I need to consider, and also I need to consider the Tzz on this field surface. Clear? Now let's calculate the field on the ball. Is it? What I need to consider first? Tell me. Calculating this T, what I need to calculate? I need to calculate the electric field. Is it? So what are the components of the electric field along x direction, y direction, and z direction? Okay, you know this is actually this charge a solid sphere. What is the electric field? What is the electric field? Let's say on the surface. So it is q square by r. Is it? Sorry, q by r square. I'm sorry. So on the surface, how much is the field? Q by r square. Is that true? So much more? So when you consider the disk, what is the electric field on the disk? So since these points are within the flash, is it? So if within the solid sphere, how the electric field varies? It's proportional to R, is it? You got my point?
Yes, sir.
Oh, so that means I have got actually the electric fields. Let's write. How much is? Okay. Okay, I will just try it. You are having charge plus q and minus q, separated by a distance 2d. Okay, what is the force of attraction between the two? Oh, no. By Coulomb's law, is it? So let's write this as a z direction. Eh? Okay, q square by 2d whole square minus. So this is the force of attraction. Now use this very formula, and this Gij. Calculate what is the force of attraction between the two charges. समझ आया? Just try to use Maxwell's stress tensor and calculate the force of attraction between 2 point charges. Okay, you'll learn something. Just try it at your places. How to do it. So it's a very. I have given actually the idea. So this idea lies here. Okay, so idea is here. That's why I started with this very problem. You can think actually one charge. There's a negative charge here, positive charge here. Okay, separated by the distance 2d. Clear? So on the surface, when you, because surface is fictitious, you can take it to infinity, is it? So the field on the surface should vanish. So surface will not contribute. Only the field along this very circle will contribute. So that is actually the dipole field. So you will be having only the z component of the field, TZZ. Only you need to calculate only TZZ. In TZZ, what is Ex will be 0, Ey will be 0. What you are getting? Ez square. Okay, then just integrate over this very circle. So that's the surface. So this is how you can do it.